Hi, everybody, and welcome to the season finale of the DI seminar. The seminar is streamed and recorded, so if you are showing yourself in the camera or you mute yourself to ask a question, which you are very free and welcome to do, you are acknowledging that we are recording you and accept to be recorded. If you are shy and don't want to be recorded, you can still ask your question in the chat and I will read it for you. So thank you all for coming. I'm happy to introduce Kasun Fernando, which is talking about expansions in mixing local limit theorems for dynamical systems. The stage is yours.
Thank you, Marcello, and thank you, Marco, for the invitation. And so today I'll be talking about expansions in the mixing local limit theorems for dynamical systems. And this was a project that we finished last year with Françoise Pène. And we had different types of results, but I chose one particular result that I think will be interesting for many people. And I'll be talking about this main result, which is where we prove some expansions for the mixing local theorems for a large class of dynamic systems. So first I will introduce what these expansions are, and then I will try to maybe motivate to some of you, you know, why should you care about these expansions? And then I will sort of introduce with certain, you know, missing details, the abstract model that we are working on. It's a bit technical, but I hope I will be able to give you enough intuition to sort of relate whatever assumptions we have to things that you already know and sort of get understand the model better. And then I will state the main result, and then I will finally sort of try to talk about some concrete examples relating how they relate to the abstract model that we work on. And there are, like, you can see the number is, there are 99 sort of slides, but it's actually with the pauses and all that. So, and I'll basically plan to cover about 20 slides, like in terms of slide numbers. So don't worry, like I think I'll be able to finish in time. So we are concerned with chaotic dynamical systems, right? So think about Fm mu, which is a chaotic probability preserving dynamical system. And we consider a centered observable, centered in the sense that the integral of the observable phi with respect to mu is 0. And we consider the Birkhoff sums, right? In a part of ergodic theory is concerned with proving limit theorems for Birkhoff sums. So this is the more limit theorems there are, the more chaotic, in some sense, the dynamical system is, right? This is something that we all agree to. So sort of my research sort of interests are in not only limit theorems, but also establishing asymptotic expansions in the sense that, you know, we want to understand precise asymptotics of these limit theorems. For example, for central limit theorem, for mixing local central limit theorem, and large deviation principles. So some of my work, my work is related to all three of these three types of limit theorems, but I will today only concentrate on the mixing local central limit theorem, right? And so what is a mixing local central limit theorem? So if you know about local central limit theorems, mixing local central limit theorems are generalizations of these local central limit theorems. And they've been used in the setting of dynamical systems to prove limit theorems of flows. And what do I mean by a mixing local central limit theorem? So we say this Birkhoff sum satisfies the mixing local central limit theorem with functions psi, z, and g if there is a constant c and some quantity that depends on the function g, right? Only on the function g, not on psi or z, such that the expectation with respect to the invariant probability measure mu of psi times g of Sn times c of Fn, right, looks like the first term here, right? The first order approximation is this, and the error is little of 1 over square root n. So the first term is of order 1 over square root n, and all the other terms are smaller order than that, right? So this is what a typical form of a mixing local central limit theorem is. So what is so why this is important? It not only keeps track of Sn, right, but also the initial. So this you can think of as psi of x, and this you can think of as c of Fn of x. So it keeps track of the initial point as well as the terminal, right? So you have more information in some sense about the behavior of the trajectories, right? So that's why it's better than the local central limit theorem, right? So if you have the local central limit theorem, both psi and z are missing. They're all equal to 1, right? So that's why we think of this as a generalization of the local central limit theorem. Okay, so we know the exact form of I. It's the integral of g, or in the case of phi being z valued, it's a sum, right? So it's some form of an integral, and then this constant c is the derivative of the normal density at 0, and this sigma in the normal distribution is the asymptotic variance of a set. Okay, right. And this is the typical form, and this is something that I said earlier. So actually we can absorb this psi to be the density of a probability measure with respect to mu, right? So but the takeaway is that mixing local central limit theorems look like this, and the first order term is of order 1 over square root. The first term is of order 1 over square root n, and the other terms of smaller order. And then our goal is to describe these small order terms, right? So this is what I mean by asymptotic expansions. So as I said, so expansions of the mixing local central limit theorem. So we say that Sn, the Birkhoff sum, satisfies the order R expansion of the mixing local central limit theorem in some function space, for some function space f, if there are polynomials Rm such that for all g in this function space, and for fixed, I mean, you have to specify function spaces for psi and z, but I don't want to get into details. But this precisely means that, okay, you have some sort of a control up to the order R, right? So you have R terms, and the error is little of 1 over square root n to the R over t. So we have some sort of a control in the asymptotics, right? So this is the typical form of expansions in the mixing local central limit theorem. Okay, so why do we care about these expansions, right? So this is an important question, because I mean, for me, initially when I started working with expansions, it was some sort of some curiosity from probability theory, right? I mean, in the classical probability theory, people have considered these expansions extensively. There's a lot of literature behind it, but then there are very important applications of dynamical systems for caring about these expansions. So let's look at some of these. So the motivation, right? So it's of course a curiosity from classical probability theory, right? So the history goes back to Chebyshev, right? End of 19th century. So people were concerned with asymptotic expansions for the central limit theorem. These are called Edgeworth expansions, right? Chebyshev, Edgeworth, and other probabilists. And then in the i.i.d. setting, of course, this was the first concern. i.i.d. setting, Kramer was the one who first proved asymptotic expansions for the central limit theorem, and then for local central limit theorem, reapproved. This was in early 2000s, reapproved expansions for the local central limit theorem, but nobody was concerned with mixing local central limit theorems. And in the Markovian setting, Nagev in 1950s proved expansions in the central limit theorem. And then also later, other probabilists have studied this for the central limit theorem and for the local central limit theorem as well. And for dynamical systems, the history goes back to 1992. Parry and Coelho proved in 1992 expansions for the CLT for non-invertible subsets of finite type. And then with Carlangelo, I proved for expanding maps and Markov chains and more general systems, but there were limitations. And for local central limit theorem, we proved expansions with Carlangelo, but also we don't have expansions for mixing local central limit theorem. So the question is, what about, like, not only expanding maps and Markov maps, can we deal with, for example, invertible maps, right? In an invertible setting, can we prove expansion? So none of the previous results applied to invertible dynamical systems. And also the observables that we used were bounded observables. Because the techniques that we used sort of in some sense were limited to bounded observables, even though it was not implicit, it was not explicit, like implicitly we had to deal with bounded observables. So can we generalize the limit expansions for limit theorems for unbounded observables? So these were two questions that we tried to answer, and we were able to give some partial answers to these questions, right? So this is sort of the output of this work with Françoise. And there was another factor, that key factor that motivated looking at these expansions, especially for the mixing local central limit theorem, because a recent work of Tima and Zhang and Kanigowski and Nandori, they were able to come up with a new mechanism for proving decay of correlations, estimating decay of correlations for suspension flows. And this is through these expansions that we prove. So they don't have any examples of systems. What they do is they work on this abstract setting where they say that if the base map of a suspension flow satisfies these expansions, and under some other extra assumptions, you can prove, one can estimate decay of correlations for these suspension dynamical systems. And they don't have concrete examples, and we were able to give the first concrete examples where their theory applies, right? So this is one of the key motivations from a perspective of dynamical systems to study these expansions. So I will sort of briefly explain this. I don't want to get into details. So if F is a map of some compact manifold preserving a measure mu, and let's say GT is a flow on a compact manifold Y preserving a measure nu, and then tau is a bounded zero mean observer. So this you can think of as the roof. And then the skew product given by this, right? We construct the skew product, preserves mu cross nu, and exhibits decay of correlations for some regular observables, provided they give a sufficient condition. The base map, of course, should have some sort of decay of correlations for some observables with some regularity. And this base map F admits a higher order mixing. I didn't introduce what global expansions are, so let's forget this global word, mixing. So let's say expansions for mixing local central limit theorems. Okay, so it's the same thing, but in the paper we use a different word, but so you don't have to worry about it. So F admits a higher order expansion for mixing local center limit theorem for tau, right? So tau is the observable in the expansion, right? And F is the dynamical system that you concerned with. And then, so you prove a expansion for the mixing local center limit theorem for Birkhoff sums of F with respect to tau, right? And then there are some assumptions about tail probabilities, which they have to verify independently of, depending on the system. But a key ingredient is this expansions to the mixing local center limit theorem, and they didn't know any sort of system for which these expansions hold, and we provide the first concrete examples, right? And this gives precise estimates on the decay correlations for the skew product, right? And I hope, did somebody ask questions so far? No, right? So I will keep the chat open in some case, and since somebody,
right. I will read the chat, don't worry.
Okay, right, okay. Right. So, I have 40 minutes. Okay, so, and there are other applications. So as soon as you have order 1 mixing expansions, you have local limit theorems for sort of shrinking targets, right? So if Ln does not decay to 0 too fast, then the probability of the Birkhoff sum belonging to some shrinking interval of length 2Ln, you have precise asymptotics for this probability. And we have deviation estimates. These are not large deviation estimates because, I mean, results about central limit theorem cannot, in principle, give results about large deviations. So this is some sort of a, one can call these moderate deviations, but some probabilists would disagree because there's a log n term. It's not n to the alpha, where alpha is larger than 1/2. But let's call these some deviations from the mean. So we have some deviation means, right? And these are important in statistical applications. For example, statistical inference and things like that. And we have this when we have mixing expansions, right? And this is discussed in my paper with Kalachilo. So these are some applications of dynamical systems, and of course, one can approach these expansions as some sort of extension of the classical theory and probability theory. So either way, there's some motivation behind studying these expansions, and I think our key motivation was this application. And when Dima asked me this question, can you prove these expansions? We got to work, and then we were able to establish these expansions for a very large class of dynamical systems. Right? So I will now describe the abstract model that we work on, and I will take some time. I think I will take maybe 20 minutes to sort of describe this abstract model in detail and try to convince you that this is a very general setup, right? So our abstract setting has 3 dynamical systems, right? They're related. This F m mu and uppercase F delta nu and F bar delta bar nu bar are 3 dynamical systems, and this F delta nu is an extension of the other 2, right? By P bar and B respectively. And so what are some examples? If you're familiar with subshifts of finite type, you can assume this P to be the identity and take this F to be the invertible subshift of finite type, and then take this to be the corresponding quotient by bunching all the negative. So if the positive terms agree, you consider all these sequences are the same, and then you quotient, and then obtain the corresponding non-invertible subsets of finite type. So you can consider it to be this. Or if you're familiar with Young towers, right, you can think of this as the mostly hyperbolic dynamical system that Young considers in her 1998 paper, and think of this as the Young tower construction, and then this as the quotient tower by quotienting along the stable leaves. Right? So this that you can think of it like that, or you can think of this as some sort of a tower constructed over this. So if you have a good dynamical system and you construct some sort of a tower by extending it, and you can consider like that, and then take this to be the identity, right? Either way. So there are many examples, many classes of dynamical systems that, that fall into this abstract setting. Of course, there are other assumptions, but at least this is not something that we cooked up like out of nowhere. This exists, this setting exists in very common hyperbolic systems, right, that dynamicists have considered earlier. And we are concerned with Birkhoff sums of zero mean observables, right? And we had two other observables, right? Z and Chi. For simplicity, let's take them to be bounded, but in reality, we can take them to be unbounded. So for example, we can take psi to be in some sort of space like this over alpha, and then this to be in L beta, where if you're considering order R expansions, you have to consider R naught strictly larger than R, and alpha beta, the sum should be less than R naught minus R, right? So you can actually consider such observables, unbounded observables, but I wanted to keep the exposition simple, so I will pick bounded observables. But if you are concerned with, if you're interested in proving things for unbounded observables, then we can deal with unbounded observables as well. And because we are using spectral techniques, we have to have a trans operator. The trans operator we are concerned with is for this system. Okay, so the quotient system. And the requirement is that this trans operator should be a nice trans operator, right? It should have some sort of spectral gap and, all the usual business in spectral theory. But there are more concerns because our initial target was to deal with this system, not this system. So by going through all these maps, we are losing some information, right? And what is the guarantee that we retain enough information to prove something about this system using the system on the left, right? So there needs to be more assumptions, right? So this is the next slide. We need more assumptions. Let's think about these. I mean, let's state these other assumptions. Did I say everything? Yes, I think that's it. So, so we need to consider phi to be non-generate. I mean, you know that central limit theorem will not hold if phi is, for example, homologous to a constant, right? The central limit theorem will be degenerate. So we need phi to be, the observable to be non-cohomologous to a constant, but we need more. We need that because we are not concerned with lattice valued random variables, we restrict ourselves to observables phi which are not cohomologous to lattice valued functions. Okay, right? So this is the first assumption, and in particular, this tells us that it can't be homologous to a constant. So if the central limit theorem holds, the variance is positive, right? There should be some other assumptions. I will state them later for this positivity. And also we should have a double chain of Banach spaces. So this is a bit technical, but if you're familiar with Keller-Liverani theorem, Keller-Liverani perturbation result, which I think was published in 1999, this paper by Keller and Liverani. So it's an alternative to the classical perturbation theory, where it's a with weaker assumptions, you get in some sense the same result of the classical perturbation theory. So this is an extension. We need a double chain of Banach spaces to extend this result to prove more general regularity properties. But this was used in 2010 by Irvi and Pène, Françoise, to prove limit theorems from Markov chains. So they were able to prove limit theorems for unbounded observables from Markov chains using the ideas of Keller-Liverani. And what we are doing is we are adapting their techniques to our setting to prove limit theorems for dynamical systems. Right? I will explain this existence of this double chain of Banach spaces in the next slide when I sort of recall the Keller-Liverani theorem. Then you will maybe understand why we require this. So this need not be L1. It can be some LP naught where P naught is greater than 1. But again, I want to keep the expression simple. In particular, if it's L1, then it holds for P naught greater than 1. So, but if it's P naught something larger than 1, it not necessarily hold for L1. So for now, let's take it to be L1. And this is one of the most important assumptions where we need to have two functions, chi and phi bar, right? Such that phi is in some sense equal to phi bar up to a co-boundary, right? And the co-boundary is given by chi, right? So this is the assumption that tells us that we can transfer information from the original dynamical system to the quotient dynamical system, right? And you would ask, okay, like why did you come up with this sort of an assumption? The motivation comes from a theorem due to Sinai when it comes for subsets of finite type. So there's a result due to Sinai that tells that up to a co-boundary, any observable that depends on up to a co-boundary with respect to the shift of finite type, subshift of finite type, any observable that depends on all the coordinates is equal to an observable that depends on the positive coordinates, right? So if you know this theorem, and this is the inspiration behind this assumption, and we can prove this, the existence of such phi bar and chi for Young towers as well, right? Young tower constructions as well. So this is not an assumption that is sort of came out of nowhere. It has some grounding in some classical results, right? So what this says, again, if I go back to the previous slide, is that phi bar is here, lives on this space. Sorry, phi is the observable, right? Phi goes from M to R, right? Real valued observable, and phi bar lives here, right? And the co-boundary, I mean, the chi lives here. So what it tells you is that information about phi can be transferred to information about phi bar up to some sort of co-boundary. And the question is whether this co-boundary term, doesn't take away a lot of information, right? I mean, we need to have enough information, and there's a technical assumption that ensures the loss of information via the co-boundary term is not much. I didn't want to state this because it's too technical, and I didn't want to sort of confuse everybody with the technical details. But if I have time, I will explicitly explain this in the case of subsets of finite time. Okay. But this is
Because let me ask a quick question.
Yeah.
That typographical symbol in the chain of Banach spaces, that inclusion.
Yeah.
Does it mean more than just inclusion? I mean compact inclusion?
Yeah. Sorry. I forgot to describe it. Sorry. Thanks for the question. Thanks. So it means that so the identity is a continuous, like a bounded operator from this to this.
Compact inclusion. Okay. Thanks.
Yeah. Right. So right. And of course we can have all to be equal, right? This is a special case. All the spaces x0 is equal to xr plus 2. In that case, what we have to do is we have to use classical perturbation theory, all right? Okay, that's a good, so I will explain it now. So that's a good time, I think, to explain this. So let's say x0 is equal to xr plus 2, then the chain collapses, right? In this case, what we should do is we should use classical perturbation theory. And if you have some experience dealing with this type of a setting, almost always we'll be dealing with Banach algebras, and almost always we will have bounded observables. So in the classical setting, so we wanted to avoid this classical setting, and we wanted to apply the Keller-Librani result through the results of Irvi and Pène, and that's why we required this chain, right? And also we require that x1, the space x1, to be compactly embedded in L2 nu bar. But of course, this is not required. This and this combined will give you that the asymptotic variance is positive. Okay, and we don't need lattice value as long as this is not cohomologous to a constant. That's good enough. Okay, right. And let's move on. There's another slide, 2 slides of assumptions. So hopefully I'll be able to finish this time. So now we are concerned with this chain of spaces, right? You can consider the chain collapsed and then just one Banach space B and read these assumptions with respect to the collapsed chain, right? But the key idea is that you consider these new operators, these perturbed operators with respect to phi bar, right? This new observable that we constructed, right, that exists under the assumptions, and these operators should be bounded operators on each of these spaces in the chain, right? And the map going from S to L sub is should be continuous as an operator valued function, right? And not only that, we need additional regularity. The additional regularity is like this. So if the difference between the spaces is j, right? Of the indices is j, then it should be Cj, right? It should be j times continuous differential, right? And the derivative, that means in particular that the derivative is a bounded linear operator from this space to this space, right? So we need a double chain because there's this, we have to apply the setting of Irvi and Pène. But I think so now we have realized, like after thinking about this paper for about a year, that we can deal with this with a single chain, and we are like trying to revise the paper now. But as of now, we don't have the proofs written down. But we can do with a single chain of spaces, but for now, let's deal with a double chain. And also we need Lasso-Tayok type inequalities, right? And for these perturbed operators. And you would ask, okay, where do these come from, right? Again, forget this assumption, and take R to be -2. It doesn't make any sense in our setting, because what do you mean by -2? What I mean is that take the case where you have only 2 spaces, along with this, right? L1. And also we need another assumption that L has a spectral gap, right? So this assume that the trans operator L, the unperturbed guy, has a spectral gap. Then what the Keller-Livrani theorem tells you is that the spectral picture of LIS, where for S small, is just like the picture of L, right? So the spectrum of L and spectrum of L sub IS, right, for small s look the same, right? For example, because this has a spectral gap, there's a leading eigenvalue, which we assume, let's say, simple. Then L sub IS will have a leading eigenvalue, which is simple, and the regularity is the regularity that we assume here, right? So if you want more regularity of this dependency with respect to S, the spectrum, the regularity of the spectrum, we need extra assumptions, and that's where this comes in, right? So the original paper of Keller and Livrani does not consider, they were not concerned with higher regularity. So this assumption is, we should credit to Irby and Pène. So this comes from Keller and Livrani, 1999, and this is due to 2010 Irby and Pène, right? So morally, what we want is the spectrum of L sub IS to look like the spectrum of L for small s, and the dependency of these spectral data, the leading eigenvalue, the eigenprojection, and everything should be regular. And this is why we require this assumption, right? Okay, hope this gives you some idea. And then this is the assumption that I said, the spectral gap assumption, right? So L acting on each of these spaces as an isolated simple eigenvalue 1, and the rest of the spectrum is contained inside the disk of radius small gap. So meaning, right, the spectrum of L looks like this. So there's a leading eigenvalue 1, and the rest of the spectrum is in some smaller disk. So this is how the spectrum, this is the complex plane spectrum of L acting on each of these spaces look like, right? Okay, and that's there. And then, you know, we will see that this gap is uniform. This gap will be larger than kappa, okay, for all of these spaces, because that's something that follows from the Lasso-Tayok inequality. Okay, right. And then we need an extra assumption. So far, good. I mean, these assumptions will give you limit theorems, but if you want expansions, you need more assumptions, because we need more control over the characteristic function of the random variables, or more control over the larger values of S, right? Not just for smaller values. So far we have some control for small values of S, but we need control for large values of S. So this is where the next two assumptions come in. So for when S is not 0, the spectrum of L sub IS should be inside the unit disk, right? And this is only for x0, x sub 0, and x0. Either one is good, right? I mean, you don't have to, like, whichever one you can prove, right? And the last assumption, I think it's the most interesting assumption and most technical in nature in some sense, is that the iterates, the iterates of the perturb trans operator for large values of S should have some control. The norm should have some sort of a control. But again, this assumption is not something that we came up with. This has been used to prove decay of correlations for suspension flows by Ergodic. So his celebrated paper in the Annals uses an estimate like this. So these are called Ergodic type inequalities. At least we choose to call them like that because these are due to him. And so he has 3 papers, one in Annals in 1998, and then 2 in Ergodic theory and dynamical systems, one in 1998, and one in 2000. So all these 3 papers deal with these type of inequalities, but with a different purpose in mind. So what he wants to prove is decay of correlations for suspension flows, but the same sort of control that he has for trans operators, we can apply in our setting to prove expansions for the mixing local center, right? So they are in some sense related. And later, these type of inequalities have been used by Melbourne, for example, to prove decay of correlations. So I think, so I will state 2 sort of conditions that they use. One is called the uni condition, uniform non-integrability condition that Ergodic uses. And then there's another condition called absence of approximate eigenfunctions. So both are introduced by Ergodic in his papers, in his early work. And these give sufficient conditions for this type of estimates to hold. Okay, so and we were able to verify these conditions for large class of observables, for young towers and subsets of finite. And what this basically tells you is that there's a sufficient control of the characteristic function of the random variables, the Birkhoff sums, these are the random variables, for S, for large values of S. So if you think about the characteristic function, right, expectation with respect to mu of e_i_Sn, right, where Sn is the Birkhoff sum, for large values of S, right, we have sufficient control. So this directly translates to an estimate for this. Okay, so this is why we need this assumption, right? And even in the i.i.d. case, we cannot escape such an assumption. For example, when Kramer proved this type of results in the i.i.d. setting, this was like a century ago, he has some assumption to control the characteristic function at infinity, and this sort of, in some sense, in the i.i.d. setting, boils down to the same assumption that Kramer had. So this is sort of a generalization, if you'd like, of the i.i.d. assumptions, right? Okay, so these are the assumptions, right? Hopefully, I was able to give you some intuition behind these assumptions. If you're familiar with work of Ergodic, then it should be clear to you what assumption 5 is. And I think this assumption is the assumption that was not present in previous literature, but all the assumptions, if you're familiar with Keller and Riverani's result, 1 and 2 are in some sense familiar. But even if you're not, you can think of the classical perturbation theory and collapse the chain and think about bounded observables with the suitable Banach space, like, for example, functions of bounded variation, Lipschitz functions, and things like that, and think about these assumptions. So in the case the chain collapses, we don't need this Lasso-Dayok inequality. We need the Lasso-Dayok inequality because we are not assuming what we assume in the classical theory. Okay, right. So the spectral assumptions, I hope, are clear. And now let's state the main results. So, okay. So do I have 2 minutes or do I have 12 minutes? Like, is it 1 hour or like 50 minutes?
No, you have 12 minutes.
Okay. All right. So yeah, I will try to be quick and state the result and maybe discuss some examples, and then I will stop. So hopefully you can recall at least some of the spectral assumptions, right? So under assumptions, the asymptotic. Oh, this is wrong. There should be a square here, and the asymptotic variance exists and is positive, and the CLT, the central limit theorem, holds with sigma squared as the variance, and the normal distribution, the resulting, limiting normal, is denoted by this symbol, right? This n sub sigma. And what our theorem says is that for G in C infinity C, the order R Edgeworth expansion holds. So remember, if you have a chain, so the chain was dependent on R, right? And the regularity was dependent on R. So if you have these results for R, then you have the order expansion. And the function space, for simplicity, I stated for compactly supported C infinity functions, but this holds for a strictly larger class of functions. The only thing we need is some sort of a decay of the function at infinity, not necessarily compactly supported. So I just stated it for compactly supported functions for simplicity, but it holds for a larger class of functions. We have exact characterization, like if you look at the paper, you will see. But the result is that we have these expansions, order expansions, under all these spectral assumptions. And these polynomials, we have the precise, exact form of these polynomials. We know how to compute their coefficients. We know their degree. We know their form. These all follow from the proof. And these expansions are unique. What else? And the coefficients depend on the asymptotic moments of Sn. Okay, so I think this correction should be there, right? And so that's the result. Okay, maybe a bit anticlimactic after all these assumptions, but some remarks, right? The first thing is that this is the first time, as far as we know, that anybody has obtained asymptotic expansions for, even in the setting of, like in probabilistic setting, nobody has considered even in for Markov chains, for example, these expansions in the maximum local central limit theorem, maybe because there was no motivation, right? Like there was no application in probability, but this is the first time these asymptotic expansions were considered, right? And this is also the first time where there are concrete examples where the setting of Ergodic and his collaborators considered, like, the concrete examples for such estimates for, a decay of correlations for suspension flows can be, considered. And this is the first time expansions have been obtained for integrability order close to that of the i.i.d. setting in a non-i.i.d. So our setting is non-i.i.d., right? We just assume that, the observables, the random variables come from a dynamical setting, right? So it's a deterministic setting, and once you condition on the present, everything is determined, like in the future, right? So where these are very much dependent, correlated, but we can still obtain the expansions for integrability order close to the i.i.d. setting. So in the i.i.d. setting, if we apply, so as I said, people have not considered for in the probabilistic setting, right? So let's take an i.i.d. sequence, then our sort of assumptions give the expansion for phi in LR2 plus. Okay. So as long as there are r+2 moments, then we are good. The random variables having r+2 moments, then we are good, right? So what we can do in the setting of Sinai billiards, for example, we can't quite get to r+2, but we can prove for a certain class of observables phi, which are r+2 plus epsilon for epsilon arbitrary small, right? So I don't want to talk about it in detail. It's a technical in nature, but we are able to get expansions for integrability order close to that of the i.i.d setting, right? And the results do hold for phi that are z-valued, for example, right? We avoided that case, but in that case, the last two spectral assumptions cannot hold. We have to replace them with appropriate assumptions. So we forget the last assumption, the Dolgopian inequality, completely, and replace the other assumption by some suitable assumption, and we can still recover these expansions for lattice-valued random variables. Okay, so these are some remarks and examples, right? Where can we apply this? What, like, or this is some abstract setting. Where can we apply this? There are a lot of examples. Sequence of i.i.d random variables, invertible and non-integrable subsets of finite type. So therefore, systems modeled by subsets of finite type, unresolved diffeomorphism, Markov maps, right? And expanding maps of the interval, not necessarily Markov maps. Multidimensional expanding maps. Systems modeled by Young towers with exponential tails, for example, Sinai billiards, Anon type attractors. Finite state Markov chains. V-geometrically ergodic Markov chains, if you know what V-geometrically ergodic Markov chains are. If not, you can think of as doubling recurrent Markov chains, right? This is a subclass, and random matrix products. So these apply for random matrix products, but also for more general group actions due to some recent results. We discussed this in our paper, but I didn't want to get into more details. So yeah, and these are, I think this gives you enough examples to show the versatility of our assumptions, right? It not only covers many hyperbolic dynamical systems, but also in systems that are very relevant in probability theory, which people have not considered before. And I wanted to talk about subsets of finite type in detail, but I don't think I will have enough time to finish it because I have only 4 minutes. So I might, stop the talk here and then maybe let the audience ask questions. I think this is a good place to stop. Yeah. Right.
Thank you very much for the nice talk.
Okay.
So
hopefully, yeah.
Are there any comments or questions?
Yeah, I apologize for the technical nature of the talk. Maybe this is not what you expected for the last seminar of the series, but yeah, hopefully
you should not apologize. So while we wait for the audience to unshy themselves, I start asking something. So in the expansions that you get for the in the polynomials that you get in the expansions, those one that you said you have a very explicit expression. Mm-hmm. Is there some information that you can recover that is somewhat telling you something interesting? For example, what is the degree of this polynomial, or what kind of structure this polynomial have? Is there something curious hidden in there?
So the form of the polynomial doesn't change from the i.i.d setting to the dependencies of the underlying system. So the underlying system does not come into the form of the polynomial, right? Form meaning, so let's say, I hope I can recall so the first polynomial is like 1 minus x squared, some constant plus another constant, something like that. I wrote it like this because, so this is the form of the polynomial. Let's say the first polynomial. Mm-hmm. And C1 and C2 depend on the underlying system and the observable phi. They do not depend on G, sorry. And they depend on psi and Z and phi. So this guy, and phi here, right? But they do not depend on G. So G is here. Okay. And the form is explicit. So if you can derive the polynomials for the i.i.d setting, those are the same polynomials. But
I see. Only the constant are changing in the way that you also were mentioning. Yeah.
Yeah. And the coefficients, we know precisely how they depend on the asymptotic moments of Sn. Right. So we have, so let's say you want to, you know that the expansion exists and you want to compute it using a computer, for example, you can find good estimates. You can find good approximations for these polynomials precisely using the system. Yeah. Trajectories of the system.
Nice. Thank you very much. Are there other comments or questions?
I do have a question, actually, in fact.
Yeah.
It's not a question about the talk, about my ignorance of what you said. So please forgive me for that. So just to make sure I understood, you mentioned that among the conditions that this function psi that appears here, just in the slide that we're seeing, shouldn't be homologous to a constant on whatever lattice you are on, right? Constant on the levels of the lattice. Yeah. So is this the right interpretation? Let me just shoot a phrase and then you tell me if I understood something or not. Because if you had a condition like that, that condition pretty much would amount to the regular local limit theorem, and that's not quite enough for your results to kick in. So you have to weaken hypothesis to work out everything that you need. Is that what it is?
No. So let's go back to the local limit theorem. Sorry. Yeah. So here, I didn't specify the nature of Sn, right? It could have been a lattice valued random variable, right? In the case it was lattice, right? It meaning phi is z valued, then necessarily Sn is z valued, right? Okay. In that case, we still have the mixing local central limit theorem, but then Ig takes a different form, right? So
okay. You mean okay. In which case, so you say in the case in which you are in a lattice, you have to use a different definition of G. So it's I mean it's okay. It's the
a different form of this. Yeah. So the form takes a it's a different form, but it's still we can have the mixing local central limit theorem.
Okay.
I don't know whether you would be inclined to call it the mixing local central limit theorem, but even if Sn takes values on a lattice, we can still have an expansion, but not under the same assumptions, because we cannot have. So, for example, we cannot have this assumption. So let me go back to this assumption. So the assumption 4, right?
Okay.
Forget this guy. Think about this characteristic function, right? So this characteristic function, if in the case of Sn being z valued, is periodic, right?
Yes.
So if it's periodic, like what happens at 0 should happen because this can be coded using, this iterated trans operator, right? So with this one, that means that if this is periodic, this cannot be non-periodic, because this should have some periodicity in the spectrum. So this cannot hold, for example.
Okay.
So we replace it with an appropriate condition and still recover the expansion. But I didn't want to complicate things. So you can still have expansions when the random variables are z valued, for example. But it's a different expansion.
Much clearer now. Thanks.
Hope I answered the question, or I don't know.
No. It's in fact very clear. I mean, you clarified the part that was confusing to me.
Okay. Okay, bye, Marcelo. Okay. Great.
So I guess I'm taking over as the host now. I'm
yeah.
So, yeah.
Are there any questions? I'm not in a hurry, so I
no. If there are no other questions, I do have another one, in fact, actually.
Yeah, I mean, I'm all ears. Like, I mean, you can ask questions if you like.
No, of course, I don't expect.
I'd be happy to answer because I want to convince people that this is something very important. I just.
I think you convince people with your last slide. Doesn't mean that people, at least, let me talk about myself.
So I forgot to tell. So,
yeah.
So, okay. So let's take, okay. So maybe for those who are waiting. So let's take the base system to be any of these things. Of course, forget this i.i.d case. Base systems to be any of this. And then you construct a suspension flow, right? According to the setting of, I had a slide, I think a complete slide about this, about the work of Zima and the others. Yeah, construct this suspension using that base system, and then verify these assumptions, and then you have some estimate on DKF correlations. But I mean, they give in their paper, in their work, some ways to verify these things, but these are something to do with this is, these are maybe some technical assumptions, but what the key ingredient they were missing was this Edgeworth. I mean, okay, forget this global Edgeworth term, the mixing expansion of order 4, but we give them examples where this holds, right? So this is important in that sense also, right? That it applies to the setting of the work of Ergodic and others, this recent work. Yeah. Okay. I don't know whether you're familiar with it, but yeah.
Okay, let me ask you maybe, I don't know if anyone in the audience has more questions. I think actually some people had to leave. Why don't we do this actually, in fact, since this has been an hour and 5 minutes.
Yeah.
Why don't we declare closed your talk and the season actually of the DinAmicI seminar. So let me thank you very, very much. And let me actually take this chance.
And thanks for the invitation. And
absolutely.
I'm glad. I mean, I'm happy to conclude the seminar series for this. Yeah.
I'm happy you're the one closing it. Actually, let me take this chance to also thank all the speakers of the season. That started in November, so it's been a long and very interesting season of seminars. And I'll just goodbye everybody, and till next year.